Hi everyone, welcome to our class. I'm Professor Wilson Kamami, and my YouTube channel is also called Professor Wilson Kamami. And in this case, today we are going to look at how we differentiate the trigonometric function. So in our previous classes, we had looked at how we differentiate using the rules of differentiation. We looked at polynomial. We have looked at how we differentiate natural exponential. At the same time, we have looked at how we differentiate by first principle. So today, we are going to look at how we differentiate trigonometric function, but you see us looking at various rules that we applied in our first class. We shall also use the first principle rule. So welcome to this class. Let's look at how we differentiate trigonometric function. Everybody knows that if you are given a trigonometric function, it's where you have a tan, sine, cosine, all those. So in this case, we want to look at how do we differentiate all those functions. So in this case, I know you know that if you are to differentiate sine x, you get cos x. Most of the people, you realize that if you are to differentiate sine x, you get cos x. How do we differentiate this one? How do we get that if you differentiate sine x is equals to cos x? Is it just something that is there? No, we need to look at this one. So let's take how we solve that one. Today I'm going to use the first principle rule on how we differentiate sine. So my function of x is equals to sine x. We want to differentiate sine x. So based on our, maybe I could have written the formula. We said if you are to get the first derivative of x, we said it will be function of limit as h approaches 0 or function of x plus h minus function of x all over h. So we said we are only apply this one. So in this case, my function of x is sine x. The function that I want to differentiate is sine x. So it's that one. So whenever I want to get the f of x plus h, this will be the same as sine x plus h. Sine x plus h. But we can be able to expand this one. We can be able to expand this one based on our trigonometry, where we studied maybe previous class. You know that this will be the same as sine x cos h plus sine h cos x. So how do we expand sine x plus h? I know that one. I'll show you how we expand this one. We said if you are given sine a plus b, we say it is sine a cos b plus sine b now cos a. That's how we expand this one. If it was minus, here could have been minus. When it comes to cos, we always say to be cos a cos b minus sine a sine b. That's how we expand cos a plus b. You go and look at that one, but at least I have highlighted on how we expand that one. So if here it was minus for cos, here could have been plus. So that's how we expand this one. So in my case, I have expanded my sine x plus h will be sine x cos h plus sine now h cos x. So in that case now, I replace in my formula f prime of x will be equals to limit as h approaches 0. So my function of x plus h will be sine x cos h plus sine h cos x minus my function of x will be minus sine x all over h. As you can see from this, we can be able to show that here and here sine is common. So we can proceed and say this is limit as h approaches 0. So sine x and sine x here is common, so I'll remove sine x. I factor out sine x, so I'll have cos h minus 1, this one and this one, because we have a common sine, plus sine h all over cos x all over everything all over h. All over h. And based in our previous class, we say that in this case, based on our previous class where we looked at how we use limits, you can be able to separate this one. So this will be the same as, because we are dealing with h, you can have sine x Now limit as h approaches 0, we'll have cos h minus 1 all over h plus, again, here we are dealing with h only, so cos x, limit as h approaches 0 of sin h all over h. Remember, in our class of limits, where we looked at limits applied in trigonometry, we said if you have cos h minus 1 all over h, we should be able to know that if you, this one will give you 0. And this one, sin h over h, will give you 1. In our previous class where we said limits applied in trigonometry. If you didn't watch that video, make an effort on looking at how now we apply limits. We called it limits applied in trigonometry. You realize that this one will be 0 and this one will be 1. So 0 times sin x, you get it is 0. So my answer will be cos x. The answer will be, because it is cos x times 1. So you realize that if you have to differentiate sin x, you get cos x. And it is very simple. You must know how we expand our sin a plus b. You must also know we are using the first principle rule. At the same time, you must know the class where we looked at limits applied in trigonometry. That's why I said in our calculus, it is good to have a follow-up. The first class we looked at introduction to calculus, where we applied rules of differentiation. Now, the second class, we looked at how we differentiate using the first principle rule, on how we use the first principle rule. So we looked at that one, and that's what we have applied. Then in the other class, we looked at how now, we looked at another class where we looked at limits. A limit, we looked at how limits are applied in exponential, how are they applied in trigonometry, and you realize that in this case, we have used now that class where we looked at limits applied in trigonometry, where it will be able to show you that this one will be 0, and this one will be able to see that this one will be 1. And that's how you get that. This is 0 times sin x, 1 times cos x, and you get cos x. So let's proceed and look at how we differentiate cos. Example 2 now, we look at how we differentiate cos x. We want to know if you differentiate cos x, you get what? So in this case again, my function of x is cos x, because I'm using the first principle rule. And what is f of x plus h? Because I want something that I will replace here, so it will be equals to cos x plus h. Cos x plus h. And we said, how do we expand cos x plus h? It's the same as here. That's why I didn't love this one. Sin a plus b, we said it is this one. But when it comes to cos x plus a plus b, you'll have here as minus. So in this case, you have cos x, cos h, minus, because this was plus, for cos now this one will be minus. It will be minus sin x, sin h. And you'll be able to see that the difference between this one and the other one is that for sine, you use sin cos, but the other one you start with cos, sin. So in that case, we'll have cos x, cos h, sin that one and sin that one. So if you have to use that now we replace in our formula, f prime will be equals to limit as h approaches 0 of function. Our function of x plus h is this one now, cos x, cos h minus sine of x, sine of h, minus, now my function of x is cos x all over h. So in this case, you realize what is common. You realize here cos x and this cos x are common. So in that case, you have limit as h approaches 0, we have cos x. Now you have cos h minus 1, because this one and this one, this is 1, minus sin x, sin h, all over h. Again, because we are dealing with limit as h approaches 0, so this one we treat as a constant, so it will be cos x. Now we have limit as h approaches 0 of cos h minus 1 all over h, minus sin x. Now we have limit as h approaches 0 of sin h all over h. Again, you realize that from this one, you realize that limit as h approaches 0 of cos h minus 1 all over h, this one will be 0. And this one will be 1. Because we said limit of h as approaches 0 of sine h over h, you realize that one will be equals to 1. So in that case, my derivative will be minus sine x. So we can be able to conclude that if you differentiate cos of x, you realize you get negative sine of x. So with that one, it's very simple. We are using the first principle rule. I know we studied that one. If you have some problem with this one, I have the same video on calculus on how we use the differentiation by first principle. Go and look at that one on how we use the first principle, because we use this formula where we replace f of x plus h and a function of x. And we have function of x is what we want to differentiate. And function of x plus h is where we have x, we replace with x plus h. Now we expand. That's the first principle. It was our second video on calculus 1. So then, on this on trigonometry, how do we expand this trigonometry? I know you studied when you studied half identity, all those, you studied all this. So how we expand that one? Again, now we use the first principle. Then we looked at limits. We have a class where we looked at limits. And we in this case, because we are studying how we differentiate trigonometry function, make sure you watch that video on how we differentiate limits applied in trigonometry. You realize this one is equals to 0 and this one will be equals to 1. That's why I started with that class, so that we can be able to proceed. So you get negative sine x. Maybe I can give an example on how we differentiate tan. How we differentiate tan x. It's our example 3 now. Our example 3 is on how we differentiate. How do we differentiate tan x? We will get what? So we need to ask ourselves, this is a bit different with the other one. Remember we said if you differentiate sin x, you get cos x. If you differentiate cos x, you get negative of sin x. Let that one be clear to everybody. Now, how do we differentiate tan x? So remember, tan x is the same as sine of x all over cos of x. So in this case, it's very simple. How do we differentiate this one? You can use the quotient rule, the rules of differentiation. So how do we differentiate this one? Derivative of tan x will be, how do we differentiate? This is like you are differentiating f over g, the one we studied in our first calculus. So we said you first of all differentiate the numerator where the denominator is constant. So we hold cos x constant, we differentiate the numerator, minus, now you hold the numerator constant, sin x, now you differentiate the denominator, cos x, all over cos x squared. Let's be known that we said when you are using the quotient rule, the order matters. That you differentiate numerator first, then you differentiate the denominator first, while putting the other one constant, and the sign here is negative. So in that case, if you differentiate, so you get cos x. If you differentiate sin x, already we know you get cos x minus sin x. If you differentiate cos x, you will get minus sin x all over cos x, cos squared of x. So in that case, cos x, here we will have cos squared of x plus, because minus and minus will be sin squared of x all over cos squared of x. And here you know cos squared of x plus sin squared of x, we always get 1. So it is 1 over cos squared of x. And you always know 1 over cos will be sec. Second, it will be sec squared of x. So we can be able to conclude that if you differentiate tan x, you will get sec squared of x. And that's the answer. How we differentiate. At least I have shown you how we use the quotient rule. That's why I said in calculus, the class keep on following what you learned before. We used quotient rule in our first class, Introduction to Calculus, Rules of Differentiation. This is quotient rule. If you remember quotient rule, you differentiate numerator first, while you hold the denominator constant, then minus, hold numerator constant, then differentiate this one, all over our denominator squared. And when you solve that one, you get, when you differentiate sin x, we said you get cos x. When you differentiate cos x, you get minus of sin x. And when you open the bracket, you get plus sin squared. And this one was cos squared. And we said sin cos squared plus sin squared, you always know will be equals to 1. So you have 1 over that one. And this one is the same. 1 over cos. 1 over cos is sec. So we have sec squared of that one of x. So that's how we differentiate tan. Maybe you can look at, now we can add here. We will be adding here. Now when you differentiate tan x, let it be known you get of x. Now we can proceed in our example 4 and look at how do we differentiate now the inverse of this, the inverse of this one now. Example 4, we look at how we differentiate cot x. Let it be known that cot x is the same as 1 over tan of x. Okay? Because we said sec is 1 over cos x. Cot x is the same as 1 over tan x. And 1 over sin x is equals cosec of x. So in this case now, we are looking at how do we differentiate cot of x. Remember, tan x, we said it is sin x all over cos x. So it means that cot x will be cos x all over sin x. Because 1 over tan, it is the reciprocal of this one, so it will be cos over sin. Because tan is sin over cos, so it means that now my cot, which is 1 over this one, will be cos over sin. So if you are to differentiate this one, we differentiate the same way, using the quotient rule. How do you use that one now? Derivative of cot x will be equals to differentiate, hold this one constant, sin x, differentiate numerator, differentiate cos x, minus, now hold the numerator constant, differentiate the denominator, and my denominator is sin x all over sin x squared. So when you differentiate this one, you get negative of cos. Negative of sin x, sorry for that. You get negative of sin minus cos x times cos of x all over sin squared of x. Because this was sin x squared when it's the same as that one. So this one you get negative of sin squared of x minus cos squared of x all over sin squared of x. So we know if you remove negative sign, we will have sin squared of x plus cos squared of x all over sin squared of x. Remember this one is 1, so we have negative 1 all over sin squared of x. And this one now is the same as negative of what? Cosec squared of x. So we can be able to conclude that if you differentiate cot x, you get negative of cosec of x. Negative of that one squared. So now, as you can see, we can be able to proceed. You can work on that one. Maybe I will show you on how we differentiate. I'll give you an example. I'll show you just how we differentiate sec of x and how we differentiate cosec of x. Maybe that will close our chapter on introduction to this one, how it is applied to this one. So let's look at how we differentiate sec of that one. Will give you on how we differentiate and how we differentiate that one, then we proceed. On example 5, it's on how we differentiate sec x. The issue is, do you know what is sec x? This is 1 over cos x. So you can differentiate that one using quotient rule. So how do you apply that one? Differentiate numerator. So you hold the denominator constant, differentiate 1. Minus, now hold 1 constant, differentiate cos x all over cos x, now this one squared. So when you differentiate 1, we said when you differentiate constant, it will be 0. So it will be cos x times 0. minus 1 times, when you differentiate cos, we said you get negative of sine x all over cos squared of x. So you realize cos times 0, it will be 0, and this negative and negative will go, so it will be sine x all over cos squared x. Maybe you can simplify this further and say this one is the same as sine x all over cos x times cos x. And you know sine over cos, so this is the same as sine x all over cos x times 1 over cos x. So you realize this one, sine over cos, it is tan x. And 1 over cos is sec x. So how we differentiate now? Sec x is the same as tan of x, sec of x. And that's how we differentiate the second of this one. So the answer now, how we differentiate sec? It will be tan x, sec x. The reason why we are doing all this is because we know we will apply this one now, where we shall be using the product rule, the chain rule, the quotient. At least you have seen how we use the quotient rule on this one. So it is good to know how we differentiate this one. So another one is where now we differentiate. Example 6 is on how we will differentiate now the cosec. How do we differentiate now? Example 6, how do we differentiate cosec of x? Remember, cosec of this one is 1 over sine x. So you apply the quotient rule again, and you'll be able to get how do we differentiate this one. Let's try to solve that one, how we solve that one. So we said cos x is the same as 1 over sine x. So how do we differentiate now? Is equals to, now we use chain rule, no, quotient rule. So first of all, you differentiate the numerator, so you hold the denominator constant. You differentiate 1, then minus, you hold 1 constant, then differentiate the denominator. My denominator is sin x all over sin x squared. So you realize that when you differentiate constant, it will be 0. So you have sin x times 0 minus 1 times, when you differentiate sine, you get cos x all over sine squared x. So the answer will be negative cos x all over sine squared x. You can simplify this one further the way you have done with the other one. So this one is the same as negative cos x all over sin x times 1 over sin x. So that when you open this one, will be sin x squared. So cos over sine, we said it is cot. It will be negative cot of x. And 1 over sine will be cosec of x. And that's how we differentiate that. So that's how it will be negative cot x cosec of x. And that's the answer. That's how we differentiate that one. So let's focus now on more examples. We have looked at how we differentiate trigonometry functions. You have seen that if you differentiate sine, you get that one, cos, that one, that way. Now, let's apply now where you find that question will not ask you that one because they know this one in your logbook and the like. So, how do we differentiate this one now? You may find that maybe you are given y is equals to sine 2x. Let me call you example A. Y is equals to sine 2x. Remember, here we said we are using what we call the chain rule. So you can say y is equals to sine u. So your u, umeifanya, it is your 2x. Your u is your 2x. And we said now, y, if your u is 2x, so your y will be sine u. So we differentiate dy with respect to u. How do we differentiate sine? We said if you differentiate sine, you get cosine. So you get cosine of u. And how do we differentiate u? With respect to x, you will get 2. Because when you differentiate 2x will get 2. So in that case, we said if you are to differentiate a chain rule now, dy now over dx, we said it will be dy over du, then du over dx. And in this case, my dy over du will be cos u times d over dx will be 2. So the answer will be 2 cos u. And my u, don't forget, it was 2x. So the answer will be 2 cos 2x. So that's how we get the derivative of that one. We said if you know how we solve this one, we say it is very simple. If you have y is equal to sine 2x You can be able to solve it direct. dy over dx will be equals to, you differentiate the way it is, you get it is cos 2x. Then you differentiate here inside, you get 2. So the answer will be 2 cos 2x. So it doesn't matter which method you use. You can use the way it is, you get the way it is, differentiate like it is one function, you get cos of that one, cos 2x, then you differentiate there inside, you will get 2. So the answer will be that one. That's how we use the chain rule. So let's try a situation where we have now, here it is x squared. It is x squared. So in a direct method now, you find that if your y is equal to sine x squared, let me return the way it was. Y is equal to sine. We said you can use this one, that dy over dx will be equals to, now, if you differentiate sine the way it is, you have cos x squared. Again, now you differentiate here inside, you will get 2x. And that's the answer. But if you have to use the wrong method of chain rule, we are using the direct method the way it is. Sine, you differentiate the way it is as a one function. You have cos of that one. Then you differentiate there inside. X squared, when you differentiate, you get 2x. But the reason why we arrived at that one is why our y was sine x squared. We let u to be x squared. So my y became sine u. We differentiated this one, du, with respect to x, and we got 2x. We differentiated y with respect to u now, we got cos u. So you are able to say that dy over dx, change in y over change in x, is change in y over change in u times change in u over change in x. So we get cos u times 2x. And my cos u, my u is x squared. So you can say it is 2x cos x squared. So that's how we solve that one. So you can be able to know when you become more familiar with this one, you realize you differentiate the way it is, you assume this is one function, sine, you get cos of that one, then you differentiate there inside. So we can take now example 3, where we have y is equals to sine x. So in this one, it's the same, simple. We are using the product rule. Product rule, so that dy over dx will be equals to, now hold x constant, differentiate sin x, plus now you hold sin x constant, you differentiate x. So in that case, we have holded our x constant, then we differentiated sin x, then we hold sin x constant, we differentiate x. So in that case, you get it is x. When you differentiate sin x, you get cos x, plus now sin x. When you differentiate x, you get 1. So the answer will be x cos x plus sin x. So we have used the product rule on solving equation related with trigonometry. Now let's solve example D. Our fourth example is where you have y is equals to sec x minus x. How do you differentiate this one? So this one we are using the subtraction rule, where we say the difference rule. So we differentiate this one by itself. How do we differentiate sec x? We said you get tan x sec x. Then how do we differentiate x? You will get 1, and that's the answer. So you may find more questions that are involving trigonometry, but somewhere. But don't forget don't lose focus. If it is product rule, treat it as a product rule. It's only that you get somewhere you are getting the derivative of sin x. If it is like this, if you are getting the derivative of sec, that way. So that's how we solve the equation related to trigonometry. Let me solve one more example, and we call it a day. I have decided to solve more 3 examples on the same. So y is equal to exponential. Y is equals to exponential to power sin x. So with this one now, we are combining exponential and trigonometry function. We said if you are given an exponential function, how do we differentiate that one? We said you get dy over dx is equals to, the equation will remain the way it is. If you remember how we solved the natural exponential, we said the equation will remain the way it is, but now you differentiate the power of it, sin x. So you get it is exponential to power sin x times now cosine of x. Because when you differentiate sin x, you get cosine of x. So the answer will be cosine of x exponential sine of x. You can arrange the way you want. So that's how we solve that one. Is a combination of exponential and trigonometry. No problem. Example 6. Y is equals to sine now exponential x. Again here, use what we call chain rule. So dy over dx, if you differentiate this one, you get negative. No, if you differentiate sine, you get cos. Then we said you differentiate there inside. Now you differentiate exponential to power x. And exponential to power x, you get cos. How do we differentiate exponential function? We said the equation will remain the way it is, but now you differentiate the power. How do we differentiate exponential? It remains the way it is, then you differentiate the power of the exponential. So in that case, you get cos of exponential x times exponential x. So you can call it exponential x, cos of exponential x. No problem with that one. Then the last example is now, my example 7 is where you have y is equals to root of cos x. So there is no difference. This is the same as cos of x to power half, the square root. So how do we differentiate that one? Dy over dx. You find that if you are to differentiate this one, we said you bring this half here, you have half, then cos x to power. Now the sign will be negative half because you less 1. Here you less 1, you will find you get negative half. Then we differentiate inside. This is not our chain rule. We differentiate now there inside, and you'll be able to get half cos x to power half, negative half times negative sine x. Because when you differentiate cos, you get negative sine. So you have negative half sine x cos x to power negative half. So that's how we differentiate trigonometry function. And you realize that the more examples we are solving on trigonometry, the more it is driving us to the previous classes. So I would like to, you viewers, make sure you watch all the videos so that you can be able to solve this trigonometry function. Because like in this case, you find here we are using chain rule. You may find in other examples where we solve, we are using quotient, product rule, and all those. So it is good you watch the first video where you look at the introduction, the rules of differentiation, and at the same time, when you are driving this one, you realize that you must realize how we solved, we were solving the derivative using natural of using the first principle rule, and you realize at the same time you need to realize to learn more on limits. So welcome. Continue subscribing for more videos on calculus, because as we continue with the differentiation, we shall look at how do we integrate when we proceed. So continue subscribing, sharing with your fellow students, wherever you are. If you are doing engineering, share with even business mathematics students, because you realize they need this introduction part of calculus, and more classes will come on regression and the others for business mathematics students. So thank you for watching.